At this exact moment, a tiny piece of data has just left your device, beginning an incredible journey across our planet. Before this sentence ends, it will travel farther than most airplanes fly in several minutes. You never see this journey, yet it happens billions of times every single second around the world. Most people think their internet comes from satellites orbiting high above Earth. It usually doesn't. But the most fascinating part isn't how data leaves your phone. It's what happens when it reaches the bottom of the Atlantic Ocean. Instead of traveling through space, our data packet is heading towards something far more surprising. The bottom of the ocean. Nearly every international message, video, and website depends on an invisible network hidden beneath these waters. At first glance, it looks like an ordinary cable, but inside, one of the greatest engineering systems ever built is at work. And inside this cable, information isn't flowing as electricity, it's traveling as light. These flashes of light carry everything from emails and phone calls to movies, games, and live video streams. But how can a strand of glass thinner than a human hair carry the world's internet? Long before the internet, sending a message across a country could take days, weeks. Everything changed when engineers learned how to send electrical signals through metal wires. For the first time, information could travel much faster than people ever could. Soon, millions of kilometers of communication cables connected cities across entire continents. But oceans remained the greatest obstacle between continents. Engineers solved this challenge by laying communication cables across the ocean floor. These early submarine cables transformed global communication, but they still had important limitations. Electrical signals lose strength over long distances, requiring frequent amplification. As the world demanded faster communication, copper cables approached their physical limits. Engineers needed an entirely new way to move information across the planet. Soon, communication evolved beyond simple electrical pulses. People wanted to send something even more complex, their voices. Inside the telephone, sound vibrations became electrical signals that could travel through copper wires. Those electrical signals traveled through growing telephone networks, connecting entire cities. As more cities connected, engineers built switching systems to route every call to the correct destination. Communication networks were becoming larger, faster, and more organized than ever before. But another revolution was quietly beginning. Computers didn't understand voices, they understood numbers. Every picture, message, and video can be broken into billions of tiny ones and zeros. These binary digits became the universal language of computers. The challenge was finding a way to move enormous amounts of digital information through existing networks. Engineers pushed copper technology further, but its physical limits were becoming impossible to ignore. Electricity moving through metal always encounters resistance. As cables become longer, electrical signals gradually become weaker. Nearby electrical equipment can also interfere with those signals. Engineers added amplifiers to restore weakened signals, but every amplifier also introduced a small amount of noise. The growing internet demanded something copper could never provide: almost unlimited bandwidth. The solution wasn't a better metal, it was something far more unexpected: perfectly clear glass. At first glance, it looks fragile, but this tiny strand can carry enormous amounts of information. Unlike copper, this cable doesn't carry electricity. It carries pulses of laser light. Those flashes of light are the internet itself, carrying messages, videos, music, and every website you visit. But how can light stay trapped inside a strand of glass for thousands of miles? That's the mystery we'll solve next. To understand why that pulse didn't escape the glass, we need to understand one of the most beautiful principles in physics. Our data packet isn't electricity anymore. It's a tiny pulse of laser light traveling through pure glass. If light reaches the edge of the glass, you might expect it to escape. But something remarkable happens instead. Rather than passing through the boundary, the light reflects back into the core. This phenomenon is called total internal reflection, and it keeps the light trapped inside the fiber. Thanks to this simple principle, light can travel for hundreds of kilometers without leaving the glass. Although it looks like a single strand, a fiber optic cable contains several carefully engineered layers. At the center lies an ultra-pure glass core where every pulse of light travels. Around the core is a layer called the cladding, designed to keep the light from escaping. Protective coatings shield the delicate glass from bending, moisture, and physical damage. Hundreds of these fibers can be bundled together inside a single communication cable. But light alone isn't information. First, it must be transformed into a language that computers can understand. Every digital file is ultimately reduced to billions of ones and zeros called binary data. Inside an optical transmitter, that binary data controls an incredibly precise beam of light. A pulse of light can represent a 1. No pulse can represent a 0. These patterns change billions of times every second, carrying enormous amounts of digital information. Engineers discovered an even smarter idea. Why send just one beam of light through the fiber? Different colors of light can travel together without interfering with one another. Each color carries its own independent stream of information through the very same fiber. It's like building several digital highways inside a single strand of glass. This technology allows one fiber to carry an astonishing amount of information every second. Even light loses energy over great distances. After hundreds of kilometers, the optical signal begins to fade. If nothing restored its strength, the information would eventually disappear into the background noise. That's why engineers place special optical amplifiers along submarine cables at regular intervals. Unlike older systems, modern amplifiers strengthen the light directly without converting it back into electricity. The signal leaves almost as strong as when it first began its journey. Thousands of these amplifiers quietly operate beneath the oceans every second of every day. Together, they keep information moving across entire oceans at nearly the speed of light. In just moments, our data packet has crossed thousands of kilometers beneath the sea. But reaching land is only part of the journey. The destination still lies far ahead. Next, our packet enters one of the most important yet least visible parts of the internet, the global network itself. From space, our planet looks divided by vast oceans, but beneath those waters lies an invisible network connecting entire continents. These cables carry nearly all international internet traffic, quietly operating far below the waves. Although they look simple from the outside, submarine cables are built to survive one of Earth's harshest environments. Every protective layer has a specific job, from resisting corrosion to shielding the delicate fibers inside. But before any cable reaches the ocean floor, engineers must first decide exactly where it should go. The shortest path isn't always the safest. The seafloor is far more complex than it appears. Engineers avoid unstable slopes where underwater landslides could damage the cable. Wide, stable plains provide a much safer path for cables that must operate for decades. Once the route is approved, one of the world's most specialized engineering vessels begins the installation. Inside the ship, thousands of kilometers of cable are carefully coiled before deployment even begins. With the route approved, the cable laying ship begins one of the most delicate operations in modern engineering. Every meter must leave the ship under carefully controlled tension to prevent damage. Too much tension could snap the cable, too little could leave dangerous loops on the seabed. Sophisticated control systems constantly adjust the cable's speed as the ship moves forward. Once released, gravity slowly guides the cable toward the ocean floor. After hours of descent, the cable finally reaches the seabed thousands of meters below the surface. In deep water, the cable usually rests directly on the ocean floor without being buried. Near coastlines, the situation changes dramatically. Here, specialized underwater plows bury the cable beneath the seabed for protection. Hidden safely below the surface, the cable is protected from anchors, fishing gear, and everyday human activity. Even the strongest submarine cables aren't indestructible. Nature and human activity can still put them at risk. Most faults happen near coastlines, where anchors and fishing equipment are far more common. Deep beneath the ocean, powerful earthquakes and underwater landslides can also damage cable routes. The moment a cable fails, engineers can detect the interruption almost instantly. By measuring the returning light, they can estimate where the fault occurred with remarkable precision. Once the fault is located, a repair ship begins another extraordinary engineering mission. A grapnel is lowered to the seabed to carefully hook the damaged cable. The damaged section is slowly lifted thousands of meters back to the surface. Engineers remove the damaged section and join the optical fibers with microscopic precision. After careful testing, the repaired cable returns to the ocean, and the flow of information begins again. After crossing an ocean, our data packet reaches dry lands, but its journey is far from over. Here, optical equipment prepares the incoming signals for the next stage of the network. Thousands of optical channels arrive together, each carrying independent streams of information. Before moving forward, our packet reaches one of the internet's most important machines. A router doesn't store your information. It simply decides the best path for every packet that passes through. But one network cannot reach the entire world alone. Networks must connect with one another. Those meeting points are called internet exchange points, where independent networks exchange traffic. Here, billions of packets are redirected every second toward entirely different destinations. The fastest route isn't always the shortest. Networks constantly adapt to changing conditions. In only a few milliseconds, our packet has already crossed several independent networks without anyone noticing. After leaving the internet exchange point, our packet enters a high-capacity backbone network built to move enormous volumes of traffic. Along the way, carrier routers continue directing traffic toward the correct destination with incredible speed. Every routing decision is based on constantly updated network information rather than fixed paths. If one connection becomes unavailable, the network quickly redirects traffic through another path. This constant adaptation helps keep the internet running, even when individual links fail. Ahead lies one of the internet's busiest destinations, a hyperscale data center. Multiple fiber routes feed into the facility, ensuring reliable connectivity even if one path is interrupted. Before reaching the servers, incoming traffic passes through another layer of high-speed switching equipment. Every component is designed with redundancies so that maintenance or failures don't interrupt the flow of data. At last, our packet reaches the servers that hold the information it has traveled so far to find. Inside the data center, the network is designed like a city, with multiple layers working together to move information efficiently. Every row of servers connects to its own high-speed leaf switch, creating the first layer of the network. Above them, powerful spine switches connect every leaf switch into one massive fabric. This architecture allows almost any server to communicate with any other server in just a few microseconds. While some traffic leaves the building, much of it stays inside, flowing between servers. The destination isn't chosen at random. The network knows exactly which server should answer the request. A load balancer directs incoming requests so that no single server becomes over. If one server becomes unavailable, another can immediately take its place. Redundancy is built into every layer, ensuring the service remains available around the clock. At last, our packet reaches the exact server chosen to process the request. The packet arrives at the server's network interface, where the request enters the computer for processing. The processor reads the request and begins determining exactly what information has been asked for. First, the processor checks its fastest memory to see whether the required information is already available. Next, the request moves into the server's main memory, where active information can be accessed almost instantly. If the information isn't in memory, the server retrieves it from ultra-fast solid-state storage. Once the information is found, the server prepares it for transmission across the internet. Large files aren't sent all at once. They're divided into thousands of smaller packets. Each packet carries its own destination information, allowing it to travel independently through the network. Before leaving the server, every packet is checked to help ensure the information arrives correctly. Now everything is ready. Thousands of packets begin their return journey carrying the information you requested. The server releases thousands of newly created packets, each carrying a small piece of the information you requested. Within microseconds, the packets spread through the data centers, switching fabric and head toward the outside world. At the network edge, high-capacity routers direct the packets back onto the global internet backbone. In an instant, the electrical signals become pulses of light once again, ready to cross continents at extraordinary speed. The destination has answered. Now the journey home begins, racing back through the same global network that carried the request. Our packets have crossed continents, but one of the hardest parts of the journey still lies ahead de las mille. The global backbone now hands the traffic to regional internet providers serving cities and communities. Every city has distribution points that direct traffic towards thousands of individual customers. The farther the packets travel, the more the network branches into smaller and smaller connections. At this point, the technology depends on how your internet service reaches your home. In a full fiber network, the optical signal remains light almost all the way to your home. Passive optical splitters divide one fiber into many connections without using electrical power. One of those fibers carries our packets directly toward a single building. Inside, an optical network terminal converts the incoming light into electrical signals for your home network. The packets have reached your home, but one final device still stands between them and your screen. Inside your router, the incoming packets are checked and forwarded to the correct device on your local network. A specialized processor decides where each packet should go within your home. Because your laptop is connected wirelessly, the router prepares the packets for radio transmission. Tiny electrical signals are transformed into carefully controlled electromagnetic waves. Although invisible to us, these radio waves now carry your data through the air. The laptop's antennas capture tiny fragments of that radio energy and convert them back into electrical signals. The wireless network card reconstructs the original digital information from the incoming radio signals. One by one, thousands of packets begin arriving exactly where they belong. The operating system places every packet into the correct order, rebuilding the original information. After traveling across oceans, continents, and countless machines, the complete message is finally ready to be displayed. Inside your computer, the processor receives the completed information and prepares it for the graphics system. The graphics processor transforms raw information into millions of individual pixels. Every frame is carefully organized before being sent to the display. A display controller delivers that information to the screen with extraordinary precision. Hidden beneath the glass are millions of tiny pixels waiting for instructions. Each pixel adjusts its brightness and color independently to help build the final image. Millions of these tiny changes happen so quickly that your eyes perceive a complete picture. What began as invisible pulses of light beneath the ocean has become the image on your screen. All of this happened in only a fraction of a second. Every click begins an extraordinary engineering journey, one that remains invisible until you know where to look. Although the packets have reached your device, the video doesn't begin playing immediately. Instead, your device briefly stores a small amount of data before showing the first frame. This temporary storage is called buffering, and it helps playback continue smoothly even if new packets arrive unevenly. Next, the compressed video enters a dedicated decoding engine inside the computer. Compression reduces file size dramatically, making modern video streaming practical across the internet. The decoder begins rebuilding complete images from the compressed information. Not every frame contains a completely new picture. Many simply describe what has changed since the previous frame. By updating only the changing parts of an image, video files become far smaller without sacrificing quality. Frame after frame is reconstructed until the original video sequence is restored. In just moments, billions of calculations transform compressed data into smooth moving images. The decoded video frames are now complete, but they still have to be synchronized before reaching the display. The display engine delivers every frame with precise timing, ensuring smooth motion without visible interruptions. Millions of pixels receive fresh instructions dozens of times every second. Working together, those tiny pixels create the moving image you experience as a seamless video. From your perspective, it all feels instantaneous. In reality, an extraordinary global machine has been working behind every single frame. Every message, every search, every photo, and every video depends on this invisible network working together. Millions of independent networks cooperate every second to keep information moving across the planet. Most of this infrastructure remains completely invisible, even though billions of people rely on it every day. What you followed was only one tiny stream of information among countless others traveling at the same moment. Every click begins a journey through one of the greatest engineering achievements humanity has ever built. It all began with a single click, and in less than a second, that tiny request crossed an entire planet, hidden beneath oceans, buried under streets, and housed inside enormous buildings. This machine never truly sleeps. It's not magic, it's not a cloud, it's engineering on a planetary scale. The next time you click a link, remember, you've just set one of the world's greatest machines into motion.